All right, so let's come back. Okay. So I think let me redo this patch. So mm-users and mm-counts. Users is for number of threads and counts is for counting number of process sharing the structure. And then in an initialization phase, actually, if we have process one has 5 threads, so process one's structure will be users, like there are 5 because there are 5 threads, and count will be 1 because there's only one process sharing this structure. Okay. So then if process one forks another process called process two. So actually in Linux, when you have multi-threading, like actually you will have one thread that code the forks and to fork another process out. So this is how Linux do the thread things. So actually here I just mentioned about only the coding thread is duplicated via copy on write. So not for like all threads will be copied out. Okay. So due to this reason, process one and process two, they still share the structure because they are using copy on write. And if before any write happens, like they will still share the structure. So like users will become 6. Okay, and counts will becomes 2. So becomes 6. The reason is for process, actually in Linux, process and thread, they are very similar idea. So users, if you want to have a very kind of specific definition here, I would say like it's just like how many executable instances they are using this structure. So executable instance including like process and threads. Okay, like these kind of things. Okay, but later on, if process 2 creates 2 threads, I mean, these 2 threads usually maybe like they're using P thread, these kind of things. So the same things, process 1 and process 2, they still share the same structure because there is no update on the VMA part. So users now becomes add because you have 2 more threads, and you can see the breakdown will be 5 from P1 and 3 from P2. Okay, and then counts still remains 2 because there's no process created. Okay. Okay, so thread share structure with its parent process. So this is just let you know, like actually threads, they will share the structure with their own process. So now if process one adds a VMA, so maybe process one codes the do-mm, and then the structure should change, right? Because if we code do-VMA, then one moment. Then if we code do-mm, then this star mm probably will get another VMA, and then the VMA structure would have insert one more VMA here with its new VMA start and VMA end. Okay, so this structure will be updated, and because this structure is updated, so the whole structure will be copied out for process one. Okay, so in this stage, because there is a write, so we do the copy. Okay, so after doing the copy, actually process one's the users becomes 5 because in the prior stage, like if we do the breakdown, process one, you have 5 users here, right? Because at the very beginning, we say process one has 5 threads, and then counts becomes 1, and because like process one is one process, okay, and process two, counts also has 1 because this structure is belonging to this process, and then there are 3 threads, so users will become 3. So 3 threads is this is the same reason for this one because like process is also a user, okay, like this. Okay, so updated VMA field triggers structure copy, then we will do the copy on write. Okay, then the structure will becomes 2 structures here. Okay, so one moment. Okay, I think there is some misleading here. So actually, there is someone asking about like in this example, like here is, oh, maybe this is better. So here are several fields here, right? And this is the VM area structure, right? So inside this structure, there are some VM start, VM dash, VM end, VM next. Okay, so actually, there are more fields here. So I think this figure is a little bit misleading, but I just want to let you know, like this probably will be one field. So I think this will be more than 4 fields. This depends on how many fields they are. Okay, so this is just for the indication part. Okay. Okay, so this is for the VMA management part. And like, okay. So next on, let's talk about some basic concept of memory management. Let's come back to talk about what is patch table. Let me give you a very brief introduction on patch table before going to the details. Okay. So here, so when the CPU is going to access the data on the memory, usually, or like in our more modern systems, CPU will first get a virtual memory, the virtual address first. Okay, so virtual address, each virtual address should first go through the TOB to find if there is a hit inside TOB. So if there is a hit, means there is already a translation result between this virtual address and the physical address. So if there is, then CPU can directly access the memory. But if it is not in the TOB, then CPU should walk through the patch table before accessing the DRAM. So you can think about if there is not in the TOB, then MMU will come to walk the patch table and then do the translation here. After doing the translation, CPU can access the patch data according to the physical address. So this is the brief concept about the patch table things. So you can think about a patch table just like a translation things between the virtual address and physical address here. So for systems with virtual memory management, or like for system having MMU, all virtual address should be converted to physical address before being accessed. So for each instruction like CPU get, it is virtual address. Okay. So patch tables take the responsibility for address translations. Okay. So each patch table comprises a bunch of add byte patch table entries. So for sure, patch table entries is PTE. So add byte is because currently I assume we are using the 60-bit systems. So 60 bits equals to add byte. Okay, so one PTE entry means 64 bits. So it means add byte. Okay. So the size of patch table is proportional to the memory size. So if you have larger memory, like if the process used larger memory, more memory, then there will be more PTEs. So one PTE means there is a translation between the virtual and physical. Okay. So Linux used the multi-level patch table here. And there is 4 level for the 64-bit systems. And I'll let you know why this is 4 levels, not other kind of levels here later. So I think one tricky thing is actually each patch table entries, they are also stored on the DRAM. So you can think about this is our DRAM, right? And here, each one is a patch frame, 4 kilobyte patch frame. So patch table is also stored in a patch frame. So inside this patch frame, there are 4 kilobyte, and you can 4 kilobyte divided by add. So maybe they are 512. There are 512 patch table entries here. Okay, so you can think about here's the first entry, second entry, third entry, and there are 512 entries in this patch frame. Okay, so this is about the patch tables things. So without optimization, CPU should access memory for looking up a patch table each time. Okay, but it is time consuming. The reason is if each time we need to do the translation, it means CPU each time should access the memory. Okay, but each memory access is usually 15 nanoseconds, or like it is around like 10 to 15 nanoseconds. But for CPU itself, it only needs 0.3 or even lower nanoseconds to finish one instruction. So if CPU frequently do the address translation, and then if each instruction, it needs to first do the address translation. Then you will take a super large overhead to do this kind of stuff. So this is why in this TOB. And TOB is a hardware cache to keep the mapping between the VA to PA in the CPU. And TOB usually is not DRAM. TOB usually is a faster SRAM. So TOB usually only needs kind of 1 to 10 nanoseconds. Usually it's 1 nanosecond. So it is kind of like 50 times faster than DRAM. Okay. So this is how TOB is so important in the CPU design. Okay, so CPU raise a patch. Oh, I think you will be a little bit curious about why we talk a lot about CPU now. Because when you are going to do the patch table walking, actually in most cases, operating system will not help on the patch table walking part, because CPU will directly walk the patch table. So this is the reason why in this stage, I'm going to let you know a little bit more about how CPU works. Okay, so CPU raise a patch fault when a process accesses a memory patch without proper preparation. So like this, there are two kind of patch faults. The one is minor patch fault. Minor patch fault means patch is already in the memory, but it's not marked in the CPU. So it just means like the virtual and physical address doesn't really link together. Okay, so this is the minor patch fault part. So for example, when you use the memory allocation to allocate a super large area, so it depends, maybe you can say, hey, I want a 1 gigabyte area. But actually, Linux will not directly, or sorry, it's not Linux. The C library will not directly give you 1 gigabyte. Because if everyone say it needs 1 gigabyte, then the memory will be very limited for all the users. So only when you really touch the memory will be allocated. So current system use the on-demand patching. On-demand means you really access the address, then operating system will allocate the patch to you. Okay, but I think this is not that accurate because not really the patch is not really allocated from the operating system. Because if you guys, let me do a little bit deeper dive into this part. Because when you are going to run your C program, actually there is a library, right? So your memory allocation, usually it interacts with the library, not the OS kernel. So you can think about is the library will first allocate a super large memory from the kernel. For example, maybe the library will first get 1 gigabyte from the kernel. But because this is a shared library, so maybe there are 10 processes that are using the same shared library. So when one process say, hey, I want kind of 10 megabyte, and it really uses 10 megabyte, then the library will allocate 10 megabyte to that process. Okay, so you can think about actually current programming library takes a lot of efforts on those kind of stuff. Because if each process is going to access the operating system, then the system performance will be so low. Because each time you are going to access a kernel, you need to switch into a kernel mode, and you need to do a lot of kernel management things. But if library can help you to cover most of the things, then library and user process, actually they are all in the user space. You don't really need to do the CPU mode switching. Okay, so actually this is a little bit more details about the user process and kernel. Okay, so how about major patch fault? So major patch fault is usually is what you learn in the undergraduate. Is the patch is not in the memory, so probably it is in the storage device. Okay, so in this case, there will be extra expensive I/O movement codes for the major patch fault. So because major patch fault usually takes longer time than minor patch fault, so it is called major. Okay. Okay, so I think this is the most important part for the virtual memory, just like how the CPU works patch table. So let me directly give you one example, and maybe you will be more kind of have more knowledge about how does it work. So let's take 64-bit system as an example. And actually, even we have 64-bit systems, that means we can address in 2 to the 64 byte. But if you do some calculation, 2 to the 64 is super huge, right? Because 2 to the 64, usually people will not use that much of memory. So in current system now, usually you only use 48 bits. But 48-bit is still super large because 2 to the 48 means there are 256 terabyte of memory. So 256 terabyte of memory, usually no matter you are using PC or servers, you're not really use that much of memory. So it is enough for current systems for using only 48 bits. Okay, so the reason why we don't use 64-bit, later you will know, because the more bits you are using, it means you need to access DRAM for more time. So fewer bits will be better, will give you better performance. Okay, I think I will explain this later. So in this example, here is 64-bit, and from 48, upper than 48, they are all unused bits. So from 48 bits to 39 bits, there are 9 bits for like PGD offset. Okay, and then 39 bit to 30 bit, they're called PUD offset. So actually PGD and PUD, they are all patch table, but there are different class of patch tables. So PGD is one class of patch table. Okay, it is called like, I think it's kind of patch global directly, something like that. And this is upper directly, middle directory, and this is patch table. And then there is patch table, there are patch offset here. So this is one level. The first level of patch table is PGD, and the second level of patch table is called PUD, and the third one is called PMD patch table, and the fourth one is patch table. Okay, so you can see like patch offset is because here are 12 bits of patch offset. So 12 bits means there are 4 kilobyte, right? 2 to the 12 is 4 kilobyte. Okay, so this patch offset is going to address like inside the patch. Just like if this is a 4 kilobyte patch, then we are going to get the first like 1 gigabyte. Then this offset is going to use to get that part. Okay. Okay, let's start from. Okay, so how CPU can work the patch table without the help from operating system? So actually, CPU doesn't need the help from operating system. CPU can do the patch table translation. Okay, so here, the key thing is there is a register in CPU called CR3 register. So CR3 register will store the base address of PGD. So what I say there is a base address is like here, PGD here is a patch table. So if we are going to get the patch table, we need to know where is the beginning, where is the start of the patch, right? As we mentioned before, each patch table is also stored on the DRAM. So we need to know the location here. So CPU can work automatically, and kernel code can also work it. So there are 2 ways to work the patch table. So in this example, I only explained how CPU can work automatically, because I think in the kernel code, it would be easier, because kernel, you can use a lot of software things to do this kind of patch table working. But CPU, there are only hardware things that they can use for working. So it is, I think CPU is a little bit harder to work the patch table. So first of all, PGD base address, it will be stored in the CPU's CR3 register. Okay, so with this register, actually you will point to the bottom of the patch global directory table. So this is the first level patch table, right? So with this PGD offset, actually we can locate which PGD entry it is. So if you still remember, each entry is only 8 byte. Okay, so this 8 byte. Okay, so this 8 byte actually you can use to get the next level patch table where it is. It is possible to locate where is the next level. So the next level will be on the bottom of the patch upper directory. So this PGD will store, hey, where is the address of the PUD? Okay. So after getting the PUD, actually there is a PUD offset here. So the offset is going to locate, okay, so where is the next label is. So PUD offset plus this base address here. Like you can get the PUD entry. So after reading the PUD entry, you will get another 64 bits. Okay. So for this 64-bit, you can get the bottom of the patch middle directory again. Okay. So with this PMD table, you are going to know where is the next label is. So you're going to use a PMD offset again. So with this PMD offset plus this PMD entry, then you can get a PMD entry here. Okay. Oh, I think here is one thing to let you know is how to do the location inside list and why there are all 9 bits. So 9 bits is because, as we say, PMD entry, PUD entry, PGD entry, they're all patch table entry. So they're all 8 byte, right? So there are 512 patch table entries in each patch table. So if this patch table is 4 kilobyte, then for each 4 kilobyte, you can have 512 8 bytes here. So if you are going to know where is the location or position for each entry, you need at least 9 bits, right? Because using 9 bits, you can do the 2 to the 9 location, right? 2 to the 9 is 512, right? So using these 9 bits, you can know where is location for this 512 patch table entry. Okay. Okay. So you just look through the 4 layers because this is the last level here. This is also 9 bits here. So with the PMD entries and then offset using the patch table offset here, you can get to the last level called the patch table. So inside the patch table, actually, inside the patch table, you can find the last patch table entry here. Okay, but this entry will only point to a patch, right? Because each entry will only point to a patch frame. So this entry is point to the patch frame owned by this patch upper directory table. And this entry will point to the patch frame related to this patch middle directly. So actually, each of the patch global directory table, this table and this table, they are super huge. They are several hundred or thousand of patch frames there. Okay, so each entry will point to different patch. Okay, so when you come to the last level here, and you get the patch address, you will directly point to a patch, right? But if we are going to know where is the data that we store in the patch, we need the last level, the patch offset here, right? So this patch offset will be 12 bits. The 12 bits, the reason for 12 bits is we are going to address in the 4 kilobyte. So 4 kilobyte, we need 12 bits, 2 to the 12 to do the addressing. So like this. After opening the patch table entries, you will see this is a 64 bits, right? Because this is 8 bytes and here is 64 bits. And then the same things, this 64 bits, actually, there are the lower 12 bits is the control bits. And then the 12 bits to the 48 bits is the physical address. And then this is reserve. So this reserve is just like this because this is unused. Okay. So physical address here is about the 48 bit to this 12 bits. Just like we are going to do the virtual to physical translation. So here is the physical address here. And then the very beginning of the 0 to 12 bits here, you will be concat together with this patch offset. So you can think about this patch offset will be placed here, replace these control bits. Then from this 0 bit to this 48 bits, it can become a new physical address. Okay, this physical address will directly point to the DRAM. Okay, so this is from given a virtual address. This one is virtual address, and then this is physical address. Okay, so we're done. We're done doing the translation. So there are 4 label translation. The first is this label, second is PUD, the third is PMD, and the fourth is patch table offset. So in this procedure, in the whole procedures, we don't really need solver, right? So all the things can be finished only using the hardware part, right? Because each part, like you get a PGD base address is because inside the CPU, there is a register here. So this plus here, the PGD-offset, this function, actually, this is not a solver function. This one is only, you are going to replace this 64 bits. You are going to replace the very beginning 9 bits by this 9 bits. Okay, so you just like do some dropping and then you can just replace this 9 bits to the tail of this, like this base address, that you can get the address here. So actually, this is what MMU really does. MMU is not really a very complex, it's not a really complex kind of hardware structure. Actually, it's just a very simple circuit to concatenate the address together. It concatenates this 64 bits with the 9 bits. So the very beginning of the 9 bits will be replaced by this PGD offset. Okay, this is what MMU does. Okay, so another thing to let you know is, so why I emphasize a lot about this CPU CR3 register is so important, because if you still remember, for patch table is each process has their own patch table, right? So if you are going to context switch to other process, you need to switch the base address. So during the context switch, there is one step is to replace the base address by maybe the other process base address. Okay, so for each patch table, for each process, they have their own patch table. And this patch table, there is a base address to be the very beginning to start the traversal. And the beginning will be put into the CPU CR3 register. Okay, so this is how it works. Okay. So there is another thing is about how about the control bits here. So actually control bits, there are several control bits here. Actually, one of the control bits is called the present bit. This is important because this is how CPU triggers patch fault. Okay, so after doing this translation from virtual memory to physical, from virtual address to physical address, actually the data is still there. CPU still doesn't really access the data. CPU only get the physical address, right? Because this is just a physical address, so CPU doesn't really access the DRAM. And before accessing DRAM, CPU will first check the control bits. Inside the control bits, if the present bit is not set, because present bit means if the data is presented inside the DRAM. So if the present bit is not set, it means the data is not in the DRAM. Okay, so if the data is not in the DRAM, probably it is in the storage device. So there is a major patch fault here. Okay, so this is how CPU triggers patch fault. CPU will check the control bits and to check about if the data is in the memory or not. If it is not, then there is a patch fault. Okay, so this is how the patch table working looks like. So I think it's a little bit quick, so do you need to do it again, like to run through the whole process again? Or maybe you guys already understand about it. Okay, so maybe I'll quickly go through it again and then to make it a little bit clearer for this part. Okay. So again, so if this is a 64-bit systems, then you have, for each address, it will be 64 bits. So for each time CPU going to run an instruction, probably the instruction would need to access some data or something else. Then the data is in a virtual address. So CPU every time will get a virtual address. And CPU needs to know where is the physical address. It means CPU needs to know where the data stored on the DRAM. So CPU needs to do this virtual to physical translation. Okay, so at the very beginning, CPU will read out the base address from its CR3 register. So this base address is also a 64-bit string. Then these bit strings will point to the button for the first level. I mean, the first level of the patch table. So PGD base address will point to the bottom of this patch table. Okay, but inside this patch table, actually, this patch table is stored on a 4 kilobyte patch frame, right? Inside this 4 kilobyte patch frames, there are a lot of patch table entries. There are a lot of PGD entries. So one of the entry will be add byte. So there will be 512 PGD entries here. So if we are going to know where is the entry that we really need, then we need to read this PGD offset out and then do the concatenation. So concatenation is look like this. Like this is the 64 bits. So the last 9 bits will be directly replaced by this PGD offset. Okay, the reason is from 64-bit to the 9 bits is used for locating where is the patch frame is. But inside the patch frame, we still need to know where the patch table entry that we are needing now. So this 9 bits is going to navigate where is the correct patch table entry that we need. So in this example, with the help of the PGD offset, we can know, oh, this is on the second PGD entry that we are now needed. So CPU will then read out the patch frame from the DRAM and then read out this PGD entry and then do some decoding things. And then CPU will know, hey, actually, inside this PGD entry, there are another 64 bits. Okay, so for this 64 bits, actually, again, the same things. The prior 48 to 9 bits will be point to a patch frame. So this patch frame stores the second label of the patch table. The second label calls the patch upper directory. So inside this patch upper directory, actually, there should be a lot of patch frames because this table will be super huge. And in the next slides, I'll show you how large it is. And then with this PGD entry, we can know where is the patch frame it is. So we find the corresponding patch frame, and then the next question is, actually inside these patch frames, there are a lot of entry, right? So we need an offset. We need an offset to navigate where is the correct entry that we need. So with this PUD offset, we can concatenate with this PGD entry again. So with this PUD offset, we can know, hey, actually the PUD entry is this one that you need. So the same thing, the PUD entry is a 64-bit bit streams. It's a 64-bit address. So this address is pointing to the third label of the patch table. And the same things, actually there are so many patch frames related to this patch table. So we need this entry to point to where is the correct patch frame that we need now. So for this patch frame is another 4 kilobyte, and inside there is 512 patch table entry. And this time we need to navigate again. So we use this PMD offset to navigate where is the next label is. Okay, so with this navigation, we can know, hey, actually this is a PMD entry that we need now. So we do the same thing, we decode it, and then we get to the last label, the patch table. So inside this patch table, actually, we still need to know where is the correct entry it is. So we use this offset to get the correct entry. Okay, so after you open this entry, I mean, they are the same. I mean, the format there will be the same. This entry, actually, they look like these things. There are 64 bits. Because I say this patch table entry, they are all 8 bytes. So for this 64 bit, for each bit, they will have different meanings here. And from 12 bit to 48 bits, it stores the physical address. Okay, so maybe if you are very confused about the prior one, actually the PGD entry, if you open up from the 9 bit to 48 bits, it is the physical address. This physical address will be pointing to the base address of the PUD table. Okay, so the thing is, because there are 0 to 12 bits, and this 0 to 12 bit actually is used to navigate where is the data inside this 4 kilobyte patch, right? So this 48 bits we're going to use as a physical address. So using this 48 bits, we can directly point to the byte in this patch. Okay, but this information can be get from this patch offset. So actually inside the patch table, we don't really need to store this part, right? We just need to know which patch it is. So this one, physical address from 12 bit to 48 bit, can only point to the patch. Okay, but inside the patch, we need the first 12 bits, and this is the virtual address can provide to us. So using this patch offset, we replace the first 12 bits, then we can get the byte inside on the DRAM like this. So we can get the data out. Okay, so the thing is, actually because the first 12 bits that is not really required for in a patch table. So Linux developers things like maybe we can play some tricks on these first 12 bits. So for each bit here, actually there are some meanings here. For example, there is a present bit. Usually just only one bit here, just like 0 or 1. If it is 0, it means the data is not in the memory. If it is 1, it means the data is in the memory, like this. So not only present bit, there are also like 30 bits. So 30 bits just like if this patch is dirty or not, if this patch is updated or not. So if the patch is outdated, then it needs to somehow need to be right back to the store device. So there is also 30 bits, and there are also a lot of other control bits, but I think it's not important for this class. So I just put the present bit here to let you know each bit there is a meaning for the patch table entry. So that is for the like how to work the patch table. Okay. Let me check how much time we have now. Okay, 10 minutes. I think it's enough. So any question for this one? I mean, for the online part, I think there are a little bit too many questions, so I will arrange it and then answer it next time. Yep. So for guys here, any question for the patch table working? Okay, so if it is clear, then let's go to the next slide. So why it is 4 label? I mean, why not 3 or like why not 5? Oh, actually it can be 5, but the reason is for each time we say we have this concatenated address will point to the DRAM. Actually, each time the CPU needs to access DRAM. So you can image if we are going to do this virtual to physical address translation, we need at most 4 DRAM access, right? So each DRAM access will take 15 nanoseconds. If you are going to do 4, it means you need 200 nanoseconds. And this 200 nanoseconds cannot be duped in a parallel way, because without getting the prior stage, without getting the prior label, you cannot get the later one. So you need to do it one by one. Okay, so it will be super expensive if you are going to do the patch table translation every time. Okay, so the reason I say at most 4 is because actually in the MMU there are several caching design. So probably it is possible like you only need to do the first 3, and the last part it is stored in a cache of the MMU. But I think this is quite too more details. So you just need to know each time when you are going to get a patch table, it is 1 memory access here. So if this is not 4 label, it is 5 label or like 6 labels, then you need to do 5 times or even 6 times of the memory access. And you probably need to do the virtual to physical address translation every time when you are going to run, when you're going to execute an instruction. Okay, so you will take super long time. Okay, and the question next is why not just not use 3 label or 2 labels, or why not just use 1 label? Okay, so the reason is here. So let's assume the page size is 4 kilobyte and there's 212 byte here. And the virtual address space size is 2 to the 48. So this is the virtual address size, 48 bits. So we have 2 to the 48 bytes that we can use for address in the virtual address. And the patch table entry size is 8 byte, right? Okay, and there are how many labels? So the key idea for this to decide how many label is here. Actually, we need to know where is the first label, right? Without knowing the first label, we cannot know the later label. Okay, but how to know the first label? I just say we store the base address inside the CPU, right? But if the first label is stored in several patch frames, then we will need a lot of register here, right? Because each register can only store 1 address. So 1 address can only point to 1 patch frame. So the key idea is the first label should be possible to fit inside 1 patch frame. It cannot be more than 1 patch frame. It can only be less than 1 patch frame. So the first label, the size of the first label can only be not more than 4 kilobyte. Okay, so this is the things that we are going to do the calculation. So like this. Let's first calculate the last label. So how to calculate the last label? Given this virtual address space is 2 to the 48, then for this 2 to the 48 virtual address space, if we divide by 2 to the 12, it means we can have that much of patches here. Okay, so 2 to the 48 divided by 2 to the 12 is 2 to the 36. So we have 2 to the 36 patch frames for the last label, right? If we are going to address in 2 to the 36 of the patch frame, then we need this large of the patch table entry size, because each patch table entry can only address 1 patch frame. So if you have 2 to the 36 patch frames, you need 2 to the 33 times 8 byte of the size of the patch table entry. So this is 2 to the 39 byte. So with this huge size, actually it's more than 4 kilobyte, right? 4 kilobyte, there's only 2 to the 12 byte. Okay, so this will not be this cannot be the one label page table translation. Okay, so let's see like this. Here is 4 kilobyte pages. Then we have 2 to the 36 pages because 2 to the 48 divided by 2 to the 12. So you have this much of the 4 kilobyte pages. But as I say, if you are going to use the CR3 to point to the base address, it should only be one page table. Sorry, the page table should only be stored in one page frame. It cannot be that much. Okay, so this is the PTE used to address this page table frame. So there are that much of PTE. Okay, so because this kind of PTE cannot fit in one page table, so we need the next label. So the next label, like you divide by 2 to the 12 again, and then you time add, like you have this much of the page table, right? So there are 2 to the 27 page table. So each page table needs a page table entry. Okay, so actually the page table entry overall for the second label will be 2 to the 27 times add. That means 2 to the 30 byte. So 2 to the 30 byte is still way larger than 2 to the 12. So we need the next label because this cannot still be fit in one page. So the next label, we do the same thing. We divide by 2 to the 12 and then time the page table size, sorry, the page table entry size. So we can get the third label. So the third label is 2 to the 12, sorry, 2 to the 18 page table here. And the PTE size is 2 to the 21 byte. So 2 to the 21 byte is still a little bit larger than 2 to the 12, but it is close. So we do another label again. So another label is like this. So the last four label, if you do the, sorry. So if you do the calculation, you will get, hey, actually, there's only like 2 to the 9 page tables here. So 2 to the 9 page table, you only need 2 to the 9 page table entry. Then each entry is 8 byte, right? So 8 byte times 2 to the 9 is 2 to the 12. So 2 to the 12 can fit in one page table, right? So we're finished. We're done here. So this is the reason why we need 4 labels. And because the last label, or like the first label, can be fit inside one page, so we can use the CR3 to point to this label. Okay, so this is how the overall translation works like. No, not translation. Why we need 4 label? Okay, is it clear? So let me do it again because this is a little bit complex. So once again, if we are going to decide why this is 4 label, then we need to know because the full translation, it starts from the base address because CPU only use one register to store the base address. And this base address can only point to one page table. So the first layer, I mean, all the PTE related to the first page table should be fit in one page frame. Okay, so this is what we are going to calculate. So let's start the calculation. So if our virtual address space is 2 to the 48, then we are going to know how many page table we are needed to address this virtual address space. So 2 to the 48 divided by 2 to the 12 is here, is 2 to the 36 pages. Okay, with this 2 to the 36 pages, actually for each page, we need this amount of PTE because each PTE can only address one 4 kilobyte page. Okay, so 2 to the 36 pages, sorry, 2 to the 36 PTE. So each PTE is 8 byte. So the overall size is 2 to the 39 byte. Okay, but 2 to the 39 byte is way larger than 2 to the 12 byte because our goal is to fit all the PTE in one page frame. Okay, so one page frame is 4 kilobytes, 2 to the 12. So 2 to the 39 is larger than 2 to the 12. So it is not possible to be the last label. Okay, so let's move on to the last 2 label. So last 2 label, we do the same calculation. If we divide by 2 to the 12, we can now get, we need 2 to the 27 page table, right? Okay, so for this 2 to the 27 page table, for each PTE, actually is 8 byte. So we need 2 to the 30 byte of the PTE. Okay, But 2 to the 30 byte of the PTE still cannot fit inside one patch frame. So this cannot be the top label. So once again, we divide by 2 to the 12 bytes, and then we times by add, we're going to get the third label. So the third label of the PTE overall needs 2 to the 21 byte. Okay. But 2 to the 21 byte, those amount of PTE size still cannot be fit into one patch frame. So once again, we do the partition. So we are going to store them inside the patch table. So actually, we need this much of patch table. Okay. Okay. Oh, sorry. I think this is not clear. I think I need to modify this patch table to patch frames. I think patch frames is a better fit here. Sorry, I think I will do some modification for this terminology. I think patch frames are easier to understand in this case. Okay. So for this amount of the 2 to the 9 patch frames, each patch frame will need 1 PTE. Okay. So overall, we can get 2 to the 12 byte. So 2 to the 12 byte is equal to the patch size. So this table, the whole amount of PTE can be fit in one patch frame. So we can use one CR3 register to point to the best address or like the first address of this patch frame. So in this case, we can know there are 4 labels here. Okay, at least we need 4 labels. I mean, it is possible to use more. You can use 5 labels or 6 labels. Okay, but at least you need 4. Okay, so this is the calculation here. Okay, I think there's only 1 minute left. It is not possible to do this advanced topic. So let's stop here and then, see you guys next week.